300 million years. That's how long scientists told us it would take for the first stars to ignite after the Big Bang. The universe needed time to cool, time to let hydrogen atoms drift together, time for gravity to work its patient magic. That's what every simulation predicted. That's what every equation demanded. Then we pointed the James Webb Space Telescope deeper into the cosmic dark than anyone had dared to look before. And we found stars that shouldn't exist. Not just a few rogue outliers, hundreds of them, thousands. Fully formed galaxies burning bright just 200 million years after the universe began. Some appearing as early as 170 million years post-Big Bang. These weren't the small, primitive proto-galaxies we expected. These were massive, mature structures. Galaxies that should have taken billions of years to assemble, sitting there in the infant universe like skyscrapers in an empty field. One astronomer looked at the data and said, "It's like finding a fully grown adult at a nursery." Another just whispered, "This changes everything." The James Webb Space Telescope, JWST, launched on Christmas Day 2021. It cost $10 billion and took 3 decades to build. It was designed to see further back in time than any instrument humanity had ever created. Scientists expected discoveries. They expected surprises. They did not expect their models of cosmic evolution to shatter on day one. The first anomaly appeared in February 2022, a galaxy designated Glass Z13. The spectroscopic analysis revealed its light had traveled for 13.4 billion years. That placed it just 300 million years after the Big Bang, uncomfortably early, but still within the realm of possibility. The team published their findings with cautious excitement. Then came Glass 11, then Sears 9 3316, then HD1, and then the floodgates opened. By mid-2023, researchers had catalogued over 40 massive galaxies that theoretically should not exist. Their redshift measurements, the cosmic fingerprint that tells us how far light has traveled, kept pushing earlier and earlier. 200 million years, 180 million years. Some measurements suggested galaxies at 150 million years post-Big Bang. Dr. Ivo Labbé from the Swinburne University of Technology didn't mince words. These galaxies are so massive, they shouldn't exist this early. They break our models. Here's why this is a crisis, not just an inconvenience. Stars don't just appear. They require hydrogen gas to collapse under gravity. That collapse takes time, millions of years for the first generation. Those first stars, called population 3 stars, had to live their entire lives, fuse hydrogen into heavier elements, explode as supernovae, scatter those elements across space, and then those elements had to coalesce into new stars. Second-generation stars, the stars we actually see. This is a slow process, agonizingly slow on human timescales, but even on cosmic timescales, there are limits. The mathematics are unforgiving. You cannot compress 1 billion years of stellar evolution into 200 million years. The physics simply doesn't allow it, except somehow it happened. One galaxy in particular haunted the research teams. They called it the Impossible Galaxy. Its mass suggested it contained roughly 100 billion stars. Our Milky Way galaxy, which has had 13.6 billion years to accumulate stars, contains somewhere between 100 to 400 billion stars. This impossible galaxy had reached comparable mass in a fraction of the time. The star formation rate required would be absurd. One researcher calculated that this galaxy would need to convert gas into stars at a rate 10,000 times faster than the Milky Way does today. Not 10 times, not 100 times, 10,000 times. The universe didn't have enough time, another astronomer stated flatly. And yet, here it is. Some scientists proposed measurement errors. Maybe the redshift calculations were wrong. Maybe dust was distorting the light signatures. Maybe these weren't galaxies at all, but some other phenomenon we'd mistaken for galaxies. But the measurements kept checking out. Independent teams verified the findings. Different instruments confirmed the redshifts. These were real galaxies, impossibly old, impossibly massive, impossibly mature, and they were breaking cosmology. To understand how deeply this discovery cuts, we need to talk about what the early universe was supposed to look like. After the Big Bang, the universe was opaque, a dense fog of hydrogen plasma, so hot that photons couldn't travel more than a microscopic distance before colliding with particles. For 380,000 years, the universe was essentially a blinding white room where you couldn't see your hand in front of your face, even if hands or faces or light-sensitive organs existed yet, which they didn't. Then came the moment cosmologists call recombination. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, light could travel. The fog cleared. The cosmic microwave background radiation, that ancient afterglow we can still detect today, emerged from this moment. But the universe wasn't done being opaque. With no stars yet burning, the cosmos entered what scientists named the Dark Ages. Hundreds of millions of years, where the universe was filled with neutral hydrogen gas, cold and dark, waiting for gravity to pull it together, waiting for the first stars to ignite. Those first stars, population 3 stars, should have been massive, hundreds of times the mass of our sun. No heavy elements existed yet to help gas clouds fragment into smaller clumps, so gravity just kept pulling material together into enormous stellar behemoths. These giant stars would have burned incredibly hot, incredibly bright, and incredibly briefly, perhaps just a few million years before exploding. When they exploded, they would have seeded the universe with the first heavy elements: carbon, oxygen, iron, silicon, the building blocks of planets, and eventually life. The second generation of stars, population 2 stars, would form from this enriched material, and eventually, after billions of years, galaxies like our Milky Way would form, spiral arms, billions of stars, structure and beauty in the long, patient accumulation of stellar populations. That was the story. That was the timeline. The JWST galaxies suggest a very different story. These galaxies show spectroscopic signatures of heavy elements. Lots of them. That means multiple generations of stars had already lived and died. The cosmic assembly line had been running at full speed, somehow compressing what should take billions of years into mere hundreds of millions. Dr. Dan Coe from the Space Telescope Science Institute put it simply. We expected to find baby galaxies. We found teenagers, fully formed, organized, mature structures that look like they've been around forever, but forever hadn't happened yet. Some of these early galaxies display disk structures, organized rotation, spiral patterns. These features require time to develop through gravitational interactions and angular momentum conservation. You can't just snap your fingers and create a rotating disk galaxy. The physics of angular momentum transfer, the gradual settling of gas into a plane, the formation of density waves that become spiral arms, these processes have timescales. Timescales the early universe didn't have. One particularly disturbing galaxy showed evidence of a central supermassive black hole. These cosmic monsters typically take billions of years to grow, feeding gradually on surrounding matter. Yet here was one, fully formed, in a galaxy that existed when the universe was barely out of its infancy. It's like the universe had a head start, one cosmologist remarked. Like someone started the clock before the Big Bang, which is nonsense, but I don't know what else to say. This discovery didn't happen in isolation. Cosmology was already facing a crisis before JWST opened its mirrors. A crisis called the Hubble tension. The Hubble constant measures how fast the universe is expanding. It's one of the most fundamental numbers in cosmology. It tells us the age of the universe, its ultimate fate, the relationship between distance and velocity on cosmic scales. And we have two completely different values for it. When we measure the expansion rate using the cosmic microwave background, that ancient light from 380,000 years after the Big Bang, and run it through our standard cosmological models, we get one number, approximately 67 kilometers per second per megaparsec. When we measure the expansion rate using nearby supernovae and pulsating stars called Cepheid variables, direct measurements of how fast galaxies are moving away from us, we get a different number, approximately 73 kilometers per second per megaparsec. That might not sound like much of a difference, but in cosmology, it's enormous. It's not a small measurement error that will go away with better instruments. Both measurements have been refined over decades. Both are incredibly precise. Both should give the same answer. They don't. This suggests one of two possibilities. Either our measurements are wrong in ways we don't understand, or our model of cosmic evolution is fundamentally broken. The JWST galaxies add fuel to this fire. If galaxies formed faster than our models predict, that suggests the early universe was denser than we thought, or gravity was stronger than we thought, or dark matter behaved differently than we thought. Any of these possibilities would affect the expansion rate. They would change the Hubble constant. Some researchers propose that dark energy, the mysterious force accelerating cosmic expansion, wasn't constant in the early universe. Maybe it was stronger then. Maybe it was weaker. Maybe it didn't exist at all in those first few 100 million years. Others suggest dark matter itself might be the culprit. Our current models assume dark matter is cold, moving slowly enough that gravity can pull it into the dense clumps that seed galaxy formation. But what if some fraction of dark matter is warm or even hot, moving at relativistic speeds? That would change how quickly structure forms. Still others point to more radical possibilities. Modified gravity theories, extra dimensions, variations in fundamental constants. The toolbox of theoretical physics gets opened, and increasingly exotic tools get pulled out. Dr. Adam Rees, who won the Nobel Prize for discovering dark energy, has been measuring the Hubble constant for decades. He's watched the tension grow from a curiosity to a crisis. In a 2023 interview, he said, "We've checked and rechecked. We've used different methods, different instruments, different teams. The tension is real. Either we're missing something about how the universe evolved, or we're missing something about how the universe works. Either way, something fundamental has to change." The JWST galaxies, with their impossible masses and impossible ages, suggest the problem runs deeper than anyone imagined. Let's get specific about why these early galaxies are impossible. Star formation is not a mystery. We understand it exceptionally well. We can watch it happening in nearby molecular clouds. We can simulate it on supercomputers. The physics is well established. A star forms when a cloud of gas collapses under its own gravity. As the cloud collapses, it heats up. Eventually, the core gets hot enough, about 10 million degrees Kelvin, for nuclear fusion to ignite. Hydrogen atoms slam together with such force that they fuse into helium, releasing enormous amounts of energy. That energy pushes outward, balancing the inward pull of gravity. Equilibrium, a star is born. But this process takes time. For a cloud of primordial hydrogen gas in the early universe, we can calculate exactly how long it takes. The initial density, the temperature, the slight gravitational perturbations that start the collapse. We know these parameters from observations of the cosmic microwave background. We can plug them into our equations and compute how long until the first stars ignite. The answer is roughly 100 to 200 million years for the first population 3 stars. Then those stars need to live their lives. For massive stars, that's perhaps 3 to 10 million years. They burn bright and die young, exploding as supernovae. Then the debris needs to cool and collapse again to form second-generation stars. Another 50 to 100 million years. Then those stars need to collect into gravitationally bound structures we'd recognize as proto-galaxies. Another 100 million years minimum. Add it up, and you're looking at 400 to 500 million years as an absolute minimum for anything resembling a mature galaxy. The JWST galaxies appeared at 200 million years or less. The numbers don't work. Dr. Garth Illingworth from UC Santa Cruz has studied galaxy formation for 40 years. He's seen models evolve, seen understanding deepen. In 2023, looking at the JWST data, he told an interviewer, "I've spent decades building these models. We've refined them with Hubble data, with ground-based observations, with simulations running on the world's most powerful supercomputers. And these galaxies just laugh at all of it. They're saying, 'Your models are toys. Reality is weirder than you thought.'" One proposal suggests the first stars were far more efficient at forming than we believed. Maybe primordial gas clouds fragmented more readily. Maybe magnetic fields we hadn't accounted for played a role. Maybe turbulence in the early universe stirred gas into clumps faster than pure gravity alone would allow. But even pushing every parameter to its absolute limit, you can't compress the timeline enough. You can't turn 500 million years of stellar evolution into 200 million. The gap is too large. Another proposal. Maybe these aren't normal galaxies. Maybe they're dark stars, hypothetical objects powered by dark matter annihilation instead of fusion. Dark matter particles colliding and destroying each other could, in theory, release enough energy to light up a structure that looks like a galaxy. Except the spectroscopy doesn't match. These JWST galaxies show the chemical signatures of nuclear fusion. They have the heavy elements that only form in supernova explosions. They're made of regular stars, born and dying through regular stellar processes, just impossibly fast. A third proposal gets more exotic. Maybe the early universe had localized regions of higher density than we thought. Pockets where the Big Bang left concentrations of matter that could collapse into galaxies much faster. This would require the universe to be lumpier in its initial conditions than our current models predict. But that creates its own problems. If the early universe was that lumpy, we should see evidence of it in the cosmic microwave background. We should detect variations in temperature that match these density fluctuations. We don't. The cosmic microwave background is remarkably smooth, almost perfectly uniform, with only tiny variations of 1 part in 100,000. Those tiny variations seed galaxy formation over billions of years. They're not nearly large enough to explain galaxies forming in hundreds of millions of years. Every solution creates new problems. Every explanation breaks something else. And then there are the quasars. Quasars are the brightest objects in the universe. They're supermassive black holes, billions of times the mass of the Sun, surrounded by accretion disks of matter spiraling inward at nearly the speed of light. The friction in these disks heats them to millions of degrees, causing them to blast out radiation across the entire electromagnetic spectrum. They're beautiful, they're terrifying, and in the early universe, they absolutely should not exist. In December 2021, astronomers discovered a quasar designated J0313-1806. The redshift placed it 670 million years after the Big Bang. The black hole at its center had a mass of 1.6 billion solar masses. Pause on that for a moment. 1.6 billion times the mass of the Sun. At 670 million years after the Big Bang, black holes grow by feeding on surrounding matter. There's a theoretical limit to how fast they can grow, called the Eddington limit. When a black hole feeds too fast, the radiation from the infalling matter pushes away additional matter, choking off further growth. It's a natural brake on black hole growth. Even if a black hole forms immediately after the Big Bang and feeds at the absolute maximum Eddington limit every single moment for 670 million years, you can calculate how massive it could grow. The answer is roughly 100 million solar masses. Maybe, pushing everything to the absolute limit, you could get to 200 million solar masses, not 1.6 billion. You're off by a factor of 8 to 16. That's not a small discrepancy. That's not a measurement error. That's a fundamental break with the physics of black hole growth. And J0313-1806 isn't alone. JWST has found multiple quasars in the early universe with supermassive black holes that shouldn't exist. Each one adds to the growing sense that something is deeply wrong with our understanding. One proposed solution: maybe the first black holes didn't form from collapsed stars. Maybe they formed directly from the collapse of massive gas clouds in the early universe. These direct collapse black holes could start with masses of tens of thousands or even hundreds of thousands of solar masses, giving them a head start. But direct collapse requires very specific conditions. The gas needs to be metal-free. It needs to avoid fragmenting into stars. It needs to collapse fast enough that it exceeds the Eddington limit during the collapse itself. These conditions are possible, but rare. You might get one direct collapse black hole per billion cubic light years. Maybe. We're finding supermassive black holes everywhere we look in the early universe. Another idea: maybe black holes can exceed the Eddington limit. Maybe in the dense, chaotic environment of the early universe, matter could fall in faster than the radiation could push it away. Super Eddington accretion. Some simulations suggest this might work. Briefly, in specific circumstances, but sustaining it for hundreds of millions of years, the numbers get uncomfortable. Dr. Xiaohui Fan from the University of Arizona, who has discovered dozens of early quasars, put it bluntly: every time we find one of these things, I think, okay, this is the limit. We won't find any earlier or more massive. And then we find something earlier, something more massive. The universe keeps breaking its own rules. All of this points toward a common culprit: dark matter. Dark matter is the invisible scaffolding of the universe. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. But it has mass, and therefore gravity. Lots of gravity. About 85% of all matter in the universe is dark matter. We know it exists because we can see its gravitational effects. Galaxies rotate too fast to hold together based on visible matter alone. Galaxy clusters bend light in ways that require far more mass than we can see. The cosmic microwave background has patterns that only make sense if dark matter dominates the universe's mass budget. Our current model called lambda CDM, lambda cold dark matter, describes dark matter as slow-moving particles that clump together under gravity. These clumps become the seeds for galaxy formation. Normal matter, the hydrogen and helium we can see, falls into these dark matter wells and forms stars. This model works beautifully for the late universe. It predicts the large-scale structure we observe, the cosmic web of galaxy clusters and filaments, the distribution of matter across billions of light years. But maybe it's wrong about the early universe. What if dark matter was different in the first few 100 million years after the Big Bang? Some physicists propose that dark matter particles could have interacted with each other more strongly in the early universe, not through electromagnetism, but through some other force we don't fully understand. These self-interacting dark matter models would allow dark matter to clump faster than standard cold dark matter. Faster clumping means deeper gravitational wells. Deeper wells mean normal matter falls in faster. Faster infall means stars form sooner. Sooner star formation means galaxies assemble earlier. It's elegant, it might work, but it creates new mysteries. If dark matter had strong self-interactions early on, why did those interactions stop? What changed? And how do we test this hypothesis when we can't directly observe dark matter at all? Another proposal. Maybe dark matter isn't a single type of particle. Maybe it's a whole ecosystem. Light dark matter particles, heavy dark matter particles, particles that interact through unknown forces, particles that decay over cosmic timescales. In this dark sector model, the early universe could have had dark matter particles that behaved very differently than the dark matter dominating the universe today. Maybe some of these early dark matter particles could even emit radiation in the dark sector, allowing them to cool and collapse faster than standard dark matter. It's speculative, it's hard to test, but it's the kind of radical rethinking that these observations seem to demand. Then there's the even more radical possibility. Maybe we've been wrong about dark matter entirely. Modified gravity theories, collectively called MOND, modified Newtonian dynamics, propose that there is no dark matter. Instead, gravity itself behaves differently on large scales than Einstein's equations predict. These theories have struggled to match observations as well as dark matter models, but the JWST discoveries have given them new life. If gravity was stronger in the early universe, or if it operated differently on small scales during the first few 100 million years, that could accelerate structure formation. Galaxies could assemble faster without requiring impossible amounts of star formation. Dr. Stacy McGaw, from Case Western Reserve University, a longtime advocate of modified gravity theories, argues dark matter has always been a placeholder. We invented it because galaxies don't behave the way Einstein's gravity says they should. But we've never detected a dark matter particle. Never seen one in any experiment. Maybe that's because it doesn't exist. Maybe gravity is trying to tell us something. The mainstream response, maybe. But dark matter explains so many different observations across so many different scales that giving it up requires an alternative that works just as well everywhere. Modified gravity theories haven't achieved that yet. Still, the conversation is shifting. The impossible galaxies are forcing cosmologists to question assumptions they've held for decades. Beyond individual galaxies and black holes, there's a larger structure problem. The universe isn't random. Galaxies aren't scattered uniformly through space. They're organized into a cosmic web. Vast filaments of galaxies stretching across hundreds of millions of light years, surrounding enormous voids where almost no galaxies exist. This structure forms through gravitational collapse over billions of years. Dark matter filaments form first, and galaxies form along these filaments, like beads on a string. We can simulate this process. Supercomputers run simulations with billions of particles representing dark matter and normal matter. They start with the initial conditions from the cosmic microwave background and let physics take over. Gravity pulls matter together. Gas cools and forms stars. Galaxies merge and grow. These simulations match the universe we observe today with remarkable accuracy. The Millennium simulation, run in 2005, used 10 billion particles and took nearly a month on a supercomputer. It recreated the cosmic web in stunning detail. But these simulations also make clear predictions about the early universe. At 200 million years after the Big Bang, the simulations show a sparse scattering of small dark matter halos, a few proto-galaxies beginning to form. Nothing organized, nothing massive. JWST shows us something very different. Some of the early galaxies we've discovered appear to be in groups, clusters even. They're not isolated objects scattered randomly through space. They're gravitationally bound to each other, orbiting a common center of mass. This requires even more time. First, individual galaxies must form. Then, they must drift together under gravity. Then, they must settle into stable orbits. You can calculate how long this takes. The timescale depends on the masses involved and the distances between them. But for the structures we're seeing, you need at least 500 million to a billion years. We're seeing them at 200 million years. Dr. Catherine Whitaker from the University of Massachusetts examined several of these early galaxy clusters and said, "It's not just that the individual galaxies formed too fast. It's that they found each other too fast. Gravity doesn't work that quickly, unless the universe was much denser in those regions than we thought possible." One team proposed that the early universe might have had primordial magnetic fields far stronger than current models predict. These fields could have guided matter into filamentary structures faster than gravity alone. But where would such fields come from? And why don't we see evidence of them in the cosmic microwave background? Another team suggested cosmic strings, one-dimensional defects in the fabric of space-time left over from the Big Bang. These theoretical objects could act as gravitational highways, funneling matter into dense concentrations quickly. Except, we've looked for cosmic strings. Multiple experiments, multiple techniques. If they exist, with the density needed to explain early galaxy formation, we should have detected them by now. We haven't. Every explanation seems to require some exotic new physics, some hidden component of the universe that conveniently does exactly what we need to explain the observations, but conveniently leaves no other traces we can detect. It's frustrating. It's exciting. It's deeply unsettling. There's another puzzle buried in the spectroscopic data from these early galaxies. They're too metal-rich. In astronomy, metals means any element heavier than hydrogen and helium. Carbon, oxygen, iron, silicon. These are all metals, forged in the cores of stars and scattered through space when those stars explode. The first generation of stars, population 3, should be metal-free. They formed from pure primordial hydrogen and helium, left over from the Big Bang. When they exploded, they seeded the universe with the first metals. The second generation, population 2 stars, would have very low metallicity, just trace amounts of heavier elements. Over billions of years, as generation after generation of stars lived and died, the universe's metallicity gradually increased. Our Sun is a third-generation star, maybe fourth or fifth. It formed 4.6 billion years ago from gas that had been through multiple cycles of stellar processing. It has relatively high metallicity. The early galaxies JWST is observing should show very low metallicity. They're so young that only 1 or 2 generations of stars could have lived and died. But the spectroscopy tells a different story. Many of these galaxies show metallicity levels comparable to galaxies billions of years old. They have significant amounts of oxygen, carbon, and even iron. That requires multiple generations of massive stars to have formed, fused these elements, and exploded. The timescale problem compounds. Not only did stars form impossibly fast, but they also lived, died, and formed new generations impossibly fast. One galaxy, designated Glass E12, showed oxygen abundance nearly 20% of the solar value. That might not sound like much, but the Sun formed 9 billion years after the Big Bang, with 9 billion years of stellar processing to enrich the interstellar medium. This galaxy existed just 350 million years after the Big Bang. Dr. Themia Nanayakara from Swinburne University analyzed the spectrum and concluded, either our entire understanding of stellar nucleosynthesis is wrong, or something about the early universe allowed stars to cycle through their lives far faster than we think possible. Stellar nucleosynthesis, the process of fusing elements inside stars, is some of the most well-understood physics we have. We can measure reaction rates in laboratories. We can observe it happening in stars today. We can model it with extraordinary precision. To be wrong about this would mean being wrong about quantum mechanics and nuclear physics at a fundamental level. The alternative is equally disturbing. What if stars in the early universe were fundamentally different? Population 3 stars should have been massive, hundreds of times the mass of the Sun. They would have burned incredibly hot and lived incredibly briefly. A 200 solar mass star might live only 2 million years before exploding. But what if they were even more massive? What if the first stars were thousands of solar masses? They would burn even hotter, fuse elements even faster, and explode even more violently. Such supermassive stars are theoretically possible, but they should be incredibly rare. The conditions required are extremely specific, yet to explain the metallicity we're seeing, we'd need them to be common in the early universe. And then there's the pair instability problem. When a star exceeds about 130 solar masses, a strange thing happens. The gamma rays in its core become so energetic that they start converting into electron-positron pairs. This removes energy from the core, causing it to collapse suddenly. The collapse releases so much energy that the entire star explodes, not leaving behind a black hole, but completely destroying itself. These pair instability supernovae should be the fate of the most massive population 3 stars. They should scatter their metals across vast regions of space, enriching huge volumes of gas. We haven't found clear evidence of pair instability supernovae in the early universe. The metallicity patterns don't quite match. The explosions should produce specific ratios of elements, and those ratios aren't what we're seeing. It's another piece that doesn't fit. Some scientists are asking a more fundamental question. What if the Big Bang itself happened differently than we thought? The standard Big Bang model has the universe beginning in an infinitely hot, infinitely dense state and expanding and cooling from there. The first fraction of a second involved exotic physics, quantum fluctuations, inflation, symmetry breaking, that we can barely begin to describe mathematically. But the basic timeline is well established, or so we thought. What if the universe had a period of accelerated structure formation immediately after the Big Bang? What if some process we don't understand seeded galaxy formation far earlier than our models predict? Inflation, the period of exponential expansion, in the first fraction of a second after the Big Bang, is already part of the standard model. It explains why the universe is so uniform on large scales. Tiny quantum fluctuations during inflation got stretched to cosmic sizes, becoming the seeds of all structure. But what if inflation didn't end uniformly everywhere? What if some regions underwent extended inflation while others stopped? This could create pockets of the universe that were denser, that could collapse into structures faster. Or what if there was a second inflation, hundreds of thousands of years after the Big Bang? A brief period of accelerated expansion that reorganized matter in ways we don't see evidence for in the cosmic microwave background. These ideas strain credibility. We have good evidence that inflation happened once, very early, and ended everywhere at roughly the same time. Adding extra inflationary periods to fix galaxy formation seems like adding epicycles to save a failing model. But desperate times call for creative thinking. Another radical proposal. What if the Big Bang wasn't the beginning? Cyclic models of the universe propose that the Big Bang was actually a bounce from a previous contracting phase. The universe has been expanding and contracting eternally, going through infinite cycles. Each bounce resets most of the structure, but maybe some information carries through from one cycle to the next. If density fluctuations from a previous cycle seeded structure formation in our cycle, that could explain why galaxies formed faster than expected. Except cyclic models have their own severe problems. What drives the bounce? How does the universe avoid maximum entropy after infinite cycles? Why does our cycle look so similar to what we'd expect from a single Big Bang? Then there's the even more speculative multiverse angle. If our universe is one of countless universes in an eternal multiverse, maybe the conditions in our particular universe were special. Maybe the fundamental constants were slightly different in the early epochs. Maybe dark matter behaved differently. Maybe gravity was stronger. These ideas are unfalsifiable, which makes many scientists deeply uncomfortable. If you can explain any observation by saying the multiverse made it that way, you've stopped doing science and started doing philosophy. Dr. Paul Steinhardt from Princeton, a pioneer of inflationary cosmology who has become one of its strongest critics, argues, we shouldn't be so quick to add more and more exotic physics to save our models. Maybe the models are wrong. Maybe the entire framework is wrong. Maybe we need to start over with different assumptions. But starting over is terrifying. The Big Bang model has been refined over nearly a century. It explains the cosmic microwave background, the abundance of light elements, the expansion of the universe, the age of the oldest stars. Throwing it out requires an alternative that explains all of those things just as well, plus the new JWST observations. No one has produced such an alternative yet. In the face of such profound mysteries, some scientists, and many more philosophers and science communicators, have raised an eyebrow-raising possibility. What if we're wrong about everything because we're not observing a natural universe at all? The simulation hypothesis proposes that our universe might be an artificial construct, a cosmic computer program running on some substrate we can't perceive. If true, the laws of physics would just be the rules of the simulation, and those rules could change. Maybe the early universe ran on different code. Maybe the programmers fine-tuned parameters to make galaxy formation happen faster. Maybe the impossible galaxies are evidence of cosmic debugging. This idea, while intellectually fascinating, is scientifically sterile. If the simulation can change its rules at will, then no observation tells us anything fundamental. Every mystery could be explained away as the simulation did it. Most working cosmologists dismiss this as a thought experiment, not a serious scientific hypothesis. But the broader point remains. we might be fundamentally wrong about the nature of reality. Quantum mechanics already tells us the universe is stranger than our intuitions suggest. Particles exist in superposition states. Entanglement links objects across arbitrary distances. The observer affects the observed. Reality at the smallest scales is probabilistic, not deterministic. What if the weirdness goes deeper? What if space-time itself is emergent, arising from more fundamental quantum information? What if the Big Bang wasn't a moment in time but a boundary condition in some higher dimensional phase space? These aren't fringe ideas. They're serious proposals from serious physicists working on quantum gravity and the foundations of cosmology. They're attempts to reconcile quantum mechanics with general relativity, to find the theory of everything that unifies all of physics, and they might have implications for the early universe. If space-time is emergent, then the extreme conditions of the early universe, where quantum effects dominate over classical gravity, might have allowed structure to form through processes that don't exist in the cooler, calmer universe we inhabit now. It's speculative, it's hard to test, but it's the kind of fundamental rethinking that the observations seem to demand. So where does this leave us? The James Webb Space Telescope continues to operate. Every week brings new observations. Every month brings new impossible galaxies, new inconvenient quasars, new data that doesn't fit the models. Cosmologists are responding in several ways. First, there's careful analysis. Maybe the redshift measurements are systematically wrong in some subtle way. Maybe dust is confusing the observations. Teams are reanalyzing the data, checking for errors, looking for alternative explanations. So far, the observations keep holding up. Second, there's theoretical work. Physicists are building new models, tweaking parameters, exploring variations on dark matter and dark energy. Supercomputers are running simulations with different initial conditions, different physics, trying to reproduce what JWST is seeing. Some progress is being made. Models with slightly different dark matter properties can produce somewhat earlier galaxies, but not early enough and not massive enough. The gap remains. Third, there's a call for new data. JWST is just one instrument. The European Space Agency's Euclid mission launched in 2023 to map the universe's structure. The Square Kilometre Array Radio Telescope is under construction. The Vera Rubin Observatory will survey the entire visible sky every few nights, catching transient events and rare objects. More data might reveal patterns we're missing. It might show that these early galaxies are even stranger than we thought, or it might provide the clues needed to understand them. Fourth, there's a philosophical reassessment. Science has been wrong before, spectacularly wrong. The Earth was the center of the universe until it wasn't. The universe was eternal and unchanging until we discovered it's expanding. Newtonian gravity was perfect until Einstein showed its limits. Maybe we're at another such moment. Maybe the cosmological framework we've built over the past century is approximately right, but fundamentally incomplete. Maybe the next generation of physicists will look back on our confusion and wonder why we didn't see the obvious answer. Whatever that answer is, it's not obvious yet. Beyond the physics, these discoveries carry profound philosophical weight. For centuries, humanity assumed we were special. The Earth was the center of creation. The sun revolved around us. The stars were fixed lights on a celestial sphere, placed there for our benefit. The Copernican revolution destroyed that assumption. We're not at the center. We orbit an average star in an average galaxy in an average part of the universe. There's nothing special about our location or our moment in cosmic history. This principle, sometimes called the Copernican principle or the principle of mediocrity, has guided cosmology ever since. The universe should look roughly the same from any vantage point. The laws of physics should work the same everywhere and at all times. But what if that's wrong? What if we do live in a special time? What if the universe was genuinely different in its early epochs, operating under conditions and physics that no longer apply? That doesn't make us cosmically important. We're still insignificant specks on an insignificant planet. But it means the universe's history might be more contingent, more path-dependent than we assumed. It means initial conditions might matter more than we thought. The specific details of how the Big Bang unfolded might have shaped everything that came after in ways we're only beginning to understand. There's also a humbling aspect to these discoveries. We've mapped the cosmic microwave background to exquisite precision. We've measured the Hubble constant to a few % uncertainty. We've catalogued billions of galaxies. We've detected gravitational waves and black hole mergers and neutron star collisions. And yet, we point our most advanced telescope at the early universe and find that we don't understand what we're looking at. Carl Sagan famously said, "Somewhere, something incredible is waiting to be known." These galaxies are that something. They're incredible. They're waiting to be understood. And the fact that they exist, that the universe can surprise us so profoundly even after decades of study, suggests we're still in the early stages of understanding reality. Let's consider some of the more radical reinterpretations of what JWST is showing us. One proposal. What if these aren't distant early galaxies at all? What if the redshift is being caused by something other than cosmic expansion? In standard cosmology, redshift equals distance equals looking back in time. Light from distant galaxies gets stretched as it travels through expanding space, shifting it toward the red end of the spectrum. The more redshifted, the further away, the longer ago the light was emitted. But there are alternative theories. Tired light models propose that light loses energy as it travels through space, not because space is expanding, but because of interactions with matter or fields. This would cause redshift without expansion. Tired light theories have been thoroughly debunked. They don't explain the time dilation we observe in distant supernovae. They don't explain the cosmic microwave background. They don't match dozens of other observations. But the JWST discoveries have caused some researchers to give them a second look. If the galaxies are closer than their redshift suggests, they wouldn't be impossibly young. They'd just be ordinary galaxies at more moderate distances. The problem is that every other piece of evidence still points to the standard expanding universe model. You can't fix one problem by breaking everything else. Another alternative, intrinsic redshift. What if some objects naturally emit redshifted light, not because they're moving away from us, but because of some intrinsic property? Quasars have long shown some anomalous redshift properties. There are cases where a quasar appears associated with a galaxy, but has a very different redshift, suggesting they're at different distances. Mainstream astronomers explain this as chance alignments or gravitational lensing, but a small minority propose that quasar redshifts might not be purely cosmological. If true, the early quasars might not be early at all. They might be closer objects with unusual properties. Again, this creates more problems than it solves. It requires inventing new physics to explain the redshift, while throwing out the well-established physics that explains everything else. Then there's the variable fundamental constants hypothesis. What if the speed of light was different in the early universe? What if the fine structure constant, which governs electromagnetic interactions, has changed over cosmic time? If the speed of light was faster in the early universe, light would have traveled further in the same time. galaxies we think are at enormous distances might be closer. Timescales would be different. Physics would operate at different rates. This is less crazy than it sounds. Some quantum gravity theories allow fundamental constants to vary. We've looked for evidence of such variation in quasar spectra across cosmic time. We haven't found convincing evidence. The fundamental constants appear to be extremely constant. If they vary at all, it's by parts per billion, not the factors of 2 or 3 needed to resolve the JWST mysteries. There's an uncomfortable question lurking beneath all of this. Why does the universe allow us to exist at all? The fundamental constants of physics appear finely tuned for the emergence of complex structures. If the strong nuclear force were slightly weaker, atomic nuclei wouldn't hold together. If it was slightly stronger, hydrogen would all have fused into heavier elements in the Big Bang, leaving no fuel for stars. If the cosmological constant, dark energy, were much larger, the universe would have expanded too fast for galaxies to form. If it were negative, the universe would have collapsed before stars could ignite. If the mass difference between protons and neutrons were different, chemistry would be impossible. If the electromagnetic force was stronger or weaker, atoms wouldn't form stable molecules. The list goes on. Dozens of parameters seem to sit in narrow ranges that allow for stars, planets, chemistry, and ultimately life. This is the anthropic principle. The universe must be compatible with the existence of observers because we exist to observe it. It's a tautology, but it has explanatory power. One explanation: the multiverse. If there are countless universes with different fundamental constants, we naturally find ourselves in one of the rare universes where those constants allow for observers. All the others exist but contain no one to notice them. Another explanation: fine-tuning by design. Some entity or process deliberately set the constants to allow for complexity. This explanation is deeply unsatisfying to most scientists because it just pushes the question back a level. Who or what did the designing? The JWST discoveries add a new wrinkle. Not only must the constants be tuned for galaxies to eventually form, but the early universe's specific conditions must have been tuned to allow the rapid structure formation we're observing. The initial density fluctuations, the ratio of dark matter to normal matter, the strength of primordial magnetic fields, if they exist, the properties of whatever dark matter is made of, all of these had to be just right. Why? If the universe is a random draw from a space of possibilities, we seem to have gotten incredibly lucky. Not just lucky enough to eventually have galaxies and stars, but lucky enough to have them form in the specific way that leads to our existence on this planet at this time. Some cosmologists find this line of reasoning troubling. It feels like giving up on finding a physical explanation. But others argue that the anthropic principle is simply a fact we have to incorporate into our theorizing. We can only observe a universe compatible with our existence. Therefore, any truly fundamental theory must explain not just the laws of physics, but why those particular laws and those particular constants. It's a humbling thought. So what comes next for cosmology as a field? The 20th century was the century of establishing the Big Bang model. We discovered the expansion of the universe. We found the cosmic microwave background. We worked out nucleosynthesis and structure formation. We built a comprehensive model that explained the universe from seconds after the Big Bang to the present day. The 21st century is becoming the century of discovering that model's limitations. Dark matter. We know it's there, but we don't know what it is. Decades of increasingly sensitive experiments have failed to detect dark matter particles. Maybe they're more elusive than we thought. Maybe they don't exist as particles at all. Dark energy, even more mysterious. The cosmological constant, Einstein's biggest blunder, turns out to be real. The expansion of the universe is accelerating, but we have no fundamental understanding of why. The measured value of dark energy is 120 orders of magnitude smaller than quantum field theory predicts it should be. The Hubble tension. The universe's expansion rate depends on when and how you measure it. This shouldn't be possible if our model is correct. And now, the JWST galaxies, structure in the early universe that shouldn't exist. Each of these problems might have a mundane explanation, but taken together, they suggest something fundamental is missing from our understanding. Several paths forward are emerging. 1. Better observations. JWST will keep observing for years, hopefully decades. Future telescopes will see even further and with even greater clarity. The Nancy Grace Roman Space Telescope will launch in the late 2020s with a field of view 100 times larger than JWST. Ground-based telescopes like the Extremely Large Telescope will achieve unprecedented angular resolution. More data might reveal patterns that explain everything, or it might deepen the mysteries. 2. New physics. Theoretical physicists are exploring modifications to general relativity, new particle physics beyond the standard model, quantum effects in cosmology, and more. Some approach might crack the problem. 3. Interdisciplinary synthesis. Maybe the answer requires combining insights from quantum information theory, condensed matter physics, mathematics, and cosmology in ways we haven't tried yet. The universe might be showing us that our disciplinary boundaries are artificial. 4. A paradigm shift. Maybe we need a truly revolutionary idea, something as transformative as relativity or quantum mechanics, something that makes us rethink the nature of space, time, matter, and causality. History suggests that when a scientific field accumulates enough anomalies, when observations persistently refuse to match theory, a revolution is coming. The Ptolemaic model of astronomy accumulated epicycles and equants trying to match observations. Then Copernicus, Kepler, and Newton swept it away. Classical physics accumulated ether drift experiments and blackbody radiation problems. Then Einstein and the quantum pioneers rebuilt physics from the ground up. Maybe cosmology is at such a moment. We began with galaxies that shouldn't exist, stars that ignited too early, structures that assembled too fast, black holes that grew too massive. We've explored the observations, the problems, and the proposed solutions. We've seen how each potential answer creates new questions, how the universe seems determined to break its own rules. Where does this leave us? With wonder, with humility, with excitement. The universe is stranger than we imagined. It's always been stranger than we imagined. Every time we think we understand it, it reveals new depths of mystery. 3,000 years ago, humans looked at the stars and saw gods and heroes. We created myths to explain the cosmos. 300 years ago, we looked at the stars and saw a clockwork universe. We believed that with enough mathematics, we could predict everything. 30 years ago, we looked at the stars and saw a comprehensible history stretching back to the Big Bang. We thought we had the broad outline figured out, with only details to fill in. Today, we look at the stars and see impossible galaxies. We see a universe that operates by rules we're still learning. We see evidence that reality is far more subtle and strange than our current models capture. And that's beautiful, because it means there's still discovery ahead, still understanding to be gained, still moments of revelation waiting for the next generation of astronomers and cosmologists. The James Webb Space Telescope has given us a gift. Proof that we don't know everything. Proof that the universe can still surprise us. Proof that the greatest scientific adventure, understanding the cosmos itself, is far from over. Those galaxies shouldn't exist, but they do. And that means reality is richer, deeper, and more wonderful than we dared to imagine. The impossible has become real. And somewhere in that impossibility lies the key to understanding not just those ancient galaxies, but the fundamental nature of existence itself. The universe is trying to tell us something. We just need to learn how to listen.